Everyone, today we will discuss about mixed design, that is from the perspective of concrete technology. And in this video we will also discuss about what is happening in the practical applications, and because whatever you go to the field there will be more kind of corrections are required based on the state. So in a detail from the scratch we will discuss about mixed design. Okay, so before that, I would like to introduce myself. I'm Dr. Sritam Sapnadarshi Sahu. I have basically completed my PhD from IIT Guwahati, and currently I'm working as assistant professor in the Department of Civil Engineering, SR University, Warangal. So, you know, when we talk about concrete, it is basically a combination of cement, fine aggregate, coarse aggregate, and water. These things are basic things from the perspective of a concrete engineer. And in this case, Portland cement, as you know, this is one of the most widely used building material, and from it is mostly used for the construction. And the concrete, as far as concrete is concerned, basically there are four ingredients, as I said: cement, that we call it as a Portland cement, water, fine aggregate, and coarse aggregate in a proportionate mixer. That's why we call it as it's a homogeneous mixer. And if we take three things: cement, water, and fine aggregate, so we call it as a mortar. And as far as concrete is concerned, mostly we take more portion or more proportion of coarse aggregate, so that at least the aggregate portion will be more compared to that of the paste volume. That's why 3/4 of aggregates are required, out of which 1/4 is a paste volume. That means in order to make it a equal volume, we require both paste as well as aggregate, so that we'll have a good combination of mixes. Apart from that, whenever we discuss about the concrete, there is one more optional ingredients are there that we call it as admixtures, that also we incorporate in the concrete. So that will also give some kind of other additional advantage, like it will also use for some kind of retarding, where you want to delay the setting process, or where you can also make this accelerate the process so that your setting will be more faster. Waterproofing, so many other cases we can also use the admixtures. So today we'll discuss mostly on the mixed design. Basically, when we talk about this mixed design, one thing comes to your mind: why do we need mixed design? Because if you need to understand the concept of mixed design, we should know why we are going to understand this concept of mixed design. Because when you are going to do this mixed design, you need to ensure what is the target strength. Because whenever you are doing some concrete, you should have a target. This, say for example, if you are targeting M20 grade of concrete, what will your target strength? Whatever the target you are going to achieve the strength if you design a M20 grade. That is why we need to ensure what is the strength of the concrete required. For that we need a mixed design. Other than that, basically why we need a mixed design is because, you know, from the previous slide we required cement, fine aggregate, coarse aggregate, and water. Again, admixture is also there. Here I am not including admixture into the picture. So these four ingredients are required basically whenever you are going to manufacture the concrete. But if I know all these ingredients are required, but I don't know how much quantity of all the ingredients I need to use it, for that also I need to use the mixed design procedure. That's why in order to optimize how much proportion or proportionate rate I am going to use, how much cement is required, how much sand is required, how much aggregate is required, or how much quantity of water I need to use, all these four ingredients I am going to bind together, and I am going to manufacture, or I am going to produce this concrete. For that I need to use how much quantity all these ingredients are required. For that reason I also need to go for this mixed design. Other than that, it will also help how, because basically mixed design, whenever we are going to do this all this procedure, we have a target, as well as like whenever we are going to target for a strength, similarly we can also target for a workability says how easily we are going to mix the concrete. You know, whenever you are going to easily you are going to mix the concrete, because concreting has also different processes are there, different steps are there, starting from the placing, compaction, and the finishing. All these things are required, then only it will ensure you will have a good workability. And later part, whenever we do all this fresh state workability is done, then the next part is the strength achievement as well as durability. So durability will also ensure the structure can withstand any kind of harsh climatic condition like weathering action or any chemical, and it has to be sustained enough so that you can also ensure the mixed design is correct. Other than that, because right now, one more concept is there, that is circular economy, because we are going to reduce the wastages. So for that also, because whenever you do the mixed design, there may be a chances more quantity of waste you may also incur. So in order to reduce the waste also, we need to understand the concept of mixed design. So these are all the following points you need to understand before you go through this mixed design procedure. So the main portion is, we need to find out how much quantity of all the ingredients is required, then only we can go for this mixed design procedure. As I said, mixed design, there are basically divided into two classes. One is your nominal mix, another is your design mix. So basically nominal mix says, say for example, you can see here it is being designed designated as M5, M7.5, M10, M15, M20, M25. Definitely one curiosity you might have, what is this M stands for? So M stands for mix, and the numeric digit is there, whether it is 5 or 7.5 or 10. It represents the characteristic compressive strength at 28 days of curing. That means how much a maximum strength you can achieve after a 28 days of curing. This much. Say for example, if you are talking about M15 grade of concrete, you may likely to get a maximum. M15 means 15 megapascal, you might likely to get that one. So that is the all meaning of this M15. Then you might have seen one more thing is, it is a ratio is predefined. That means if I talk about one particular ratio M15 grade, you can see it here 1:2:4. So what does it indicate? It indicates 1 is 1 part of cement is going to mix with the 2 parts of fine aggregate and 4 parts of coarse aggregate as required, then only you can design a M15 grade of concrete. So that is why it is a nominal mixes. We cannot go for a like a design mix. In that case of, say for example, design mix, there are many more parameters we need to consider. That's why if it is a very small scale and it is not structurally, or you are not going to design for a big mega structure, for that case for a small scale you can go with this nominal mix. But if you are really interested for a building and you are going to like a good structural strength you need, then you have to go for a design mix. We'll also come back when we are going to, what are all the differences are there, or what are all the drawbacks are there in the mixed design, nominal mixed design, because in this particular lecture we are going to discuss more about the design mix part. We are not going to consider the nominal mix part, because nominal mix is, you can see in the previous slide that it is a limited with M25, because structurally if I want to design M30 or M35 or M40 or a very high grade M100 if I want to target, I cannot go with this nominal mix, because it has a limited with M25 grade of concrete, M20 or M25 grade of concrete. That is why there are many drawbacks are there in the nominal mix are there. That is why we are going to shift from the nominal mix to the design mix, because nominal mix, it has certain limitations. We cannot proceed with the nominal mix, because nominal mix, as you see, it has a fixed proportion. Say for example, we discussed M15 grade, it has to be 1:2:4. The ratios are predefined. That means the quality of the material is required, because there may be a chances the site, the aggregate you might have kept outside, there may be some kind of moisture may ingress. So all these things, there will be some kind of changes with the mixed proportion will be there. So that will also encounter fresh state properties or strength you may not get. That is why there is a drawback in the nominal mix. And the most important thing in the nominal mix, the major problem is, we are not going to consider the any kind of moistures. That means any kind of environmental exposure conditions. There are different exposure conditions are there, mild conditions are there, severe conditions are there, whether you are designing for normal concrete or you are designing for reinforced concrete. So all these things are not been inclusive in the nominal mix design. Other than that, in the nominal mix, generally we are going to compensate, because there are many kind of like approximate you are going to do. That means water cement ratios are there, you are going to approximately, you are going to, based on your visual observation, you are going to use that one. So that leads to requirement of more quantity of cement you are going to use it. And if you want more cement into your mix, the problem it will arise, the cost will also incur in a higher. And the second thing is, if you are going to use more cement into the mix, the problem is you are going to incorporate more kind of carbon, or the carbon emission will be more. So that is why there are some kind of drawbacks in the nominal mix design. Other than that, you will also encounter some kind of low accuracy. Why? Because as the water cement ratio, that is how much quantity of water is required, it is a approximate method. That means from a visual observation you are going to add that one. So that is why you may likely to get a lesser strength. You may also have a lesser accuracy. Whatever the target you are achieving, you may not get that one. And the for most thing is, whenever we are, say for example, as the water cement ratio is quietly unknown for this all the batches, so that's why today you do the mix design for this nominal mix, say for example a random water to cement ratio, and next day you do it, there will be a fluctuation with the strength value as well as the any kind of, say for example you are targeting some kind of workability, or you may target for a strength of different days, so you will have some kind of variabilities are there. So that leads to reduce your strength, that leads to reduce your accuracy level. So for that all this reason we are not going to consider the nominal mix. And the foremost thing is, in the nominal mix, the lower grade of concrete is typically we need to consider for M20 grade. If you need to design for a higher grade, you cannot do it with this nominal mix design. For that you need to go for a mix design method. So design mix method. So we are going to focus much more in the design mix part in this particular lecture. So let's take an example of that one. So in this case, it is given a question, grade of concrete is being given to you. It is M40 grade of concrete you are going to do. And in this type of cement, it is given PPC type cement. That means Portland pozzolana cement you are going to use for your particular manufacturing of the concrete. And maximum nominal size of the aggregate is also being given, that is 20 millimeter size of aggregate you are going to use it. Okay. And exposure condition, as I said, RCC design mix, the major advantage is the exposure condition also it is taking into the picture. However, the nominal mix it never takes into the picture. That is why more chances of irregularities with the respect to the strength values you may likely to get. And here in this question it is giving exposure condition is severe RCC, and workability is also given, because where in the last design nominal mix we have seen there is no kind of workability, water cement ratio values are not approximately you are going to use it, but in this case you have to have a target water to cement ratio as per your requirement. So here in this case it is given workability is 75 millimeter. And method of concrete placing, it is giving non-pumpable chute method is there. Type of aggregate, you are going to use crushed angular aggregate. Maximum cement content without fly ash, because when you are using PPC cement, Portland pozzolana cement, some part of your fly ash or mineral admixture is being added into that one. So that is why it is given in the question, maximum cement use is permissible without fly ash is 450 kg per meter cube as per the question. And chemical admixture is given, super plasticizer and normal. So basically the role of this chemical admixture is, like if sometimes what happen, we need to add more quantity of water. So without adding more water demand, we can also compensate the extra water by using this chemical admixtures. So it has a more water retention is there. There are super plasticizers, are various different classes are there, melamine type, naphthalene type, polycarboxylic ether type. So here in this case, super plasticizer is SP super plasticizer, it is giving normal. That means normal means it has a water retention of 23%. Degree of site control is good. Other than that, test materials, the data is also given. Other than that, we cannot do this mix design. So all the specific gravity data is required. So specific gravity of cement is given 2.88. Specific gravity of coarse aggregate is given 2.74. SSD condition, that means saturated surface dry condition it is given. And specific gravity of fine aggregate is also given 2.65 SSD. Chemical admixture, it is given 1.145. Water absorption of coarse aggregate is given and fine aggregate is given correspondingly 0.5% and 1%. Moisture content is given nil, but for both the coarse aggregate as well as the fine aggregate. And sieve analysis it is given for the fine aggregate zone 2. So all this data is required, then only you can go for this mix design. And in this case, we are going to see this mix design based on IS code provision 10262/2019. That is the latest edition. So let's see how we are going to proceed with the step-by-step procedure from the mix design. So in this case, your first step is you need to find out the target strength, because if it is given I need to design a M40 grade of concrete, but in that case what is my target strength I may likely to achieve. So that is why the first step is you need to calculate the target strength. So the formula is F-CK equals to FCK plus 1.65 into S. So what is F-CK? F-CK is none other than it is your target strength. What is the strength you are going to target for this? FCK, that means what is the design. M40 it is given in the question, 40 you are going to design for that. So FCK value is 40. and S stands for your standard deviation value. So that all these values are given. You can refer this IS 10262 table number 2. You can get that one. I will also show that one. Say for example, this is also given. Say for example, as I said, you are going to target for M40 grade. So what is the corresponding value standard deviation? You can see this is 5. That's why 1.65 multiplied by 5. So you are getting your target strength is 48.25 Newton per millimeter square. Or you have another formula is F dash Ck equals to Fck plus X. What is X? X stands for the factor associated with the grade. So here we are designing for M40 grade. So what is the target? So M40 grade, what is the X value is 6.5. So similarly here 40 plus 6.5, you are getting 46.5 Newton per millimeter square. As it has two values are there. One is F dash Ck equals to Fck plus 1.65 into S, or F dash Ck equals to Fck plus X. So out of these two, which value is higher, you consider that as your target star, because we need to target a higher value. So that is why from this two, as 48.25 Newton per millimeter square is higher value, therefore we have taken the target strength is 48.25 Newton per millimeter square. So in that your first step is done. Then coming to the second step, I need to calculate the air content, because we are also giving, because as normal concrete you are designing. So in that case, there will be some minute kind of air will be also be entrapped in the concrete, because aggregate will have a natural some kind of voids are there. So because of that, so what happened in the mixed design also, we need to calculate how much approximate percentage of air is also present in your concrete. In this case, we need to refer table number 3. So in this question, you have given a nominal maximum size of aggregate is given 20 millimeter size. So the corresponding value will giving you the air void, how much percentage of or the approximate air content is. You can see from 20 mm maximum size of aggregate, your corresponding value is 1%. So you are getting approximate your air content is 1%. So your step 1 and step 2 is completed by that. Next, we need to calculate. These are all the reference table 1 and table 2. So from that you can use this value of standard deviation and X value in order to get your target strength, as well as the table 3 is required for your air content value. Then we will target for the step 3. So step 3, you need to calculate the water to cement ratio, because that is the most important one, because in the previous nominal mixed design, this water to cement ratio is not being considered. So that is why approximately you have to take some value and you have to do the mix design. But in this case, design mix, we have a dedicated step for the selection of water to cement ratio. So how you are going to do that? Let's see from this. So as you have already calculated, you're in the first step, you have already calculated what is the target strength. So here in my case, my target strength is 48.25 Newton per millimeter square. So I need to check the figure number 1. So how I will check? You can see X axis, you have a free water to cement ratio, that I am going to find out. And the Y axis, it is giving the 28 days compressive strength of concrete. So what is my target compressive strength? My target compressive strength is somewhere 48.25 Newton per millimeter square. So say for example 48 means it is somewhere here. So you can see here in this particular graph, you have curve 1, curve 2 and curve 3. You might have doubt which curve I need to consider. So there is a simple guideline is there. In that case, if you need to take curve 1, you must have a target strength, whatever you have targeted or whatever you got it from your step 1. If it is within that range of 33 to 43 megapascal, so in that case you can consider the curve 1. Similarly, if your target strength lies between 43 and less than 53, you have to consider the curve 2. And if your target strength is exceeding 53 megapascal or Newton per millimeter square, in that case you have to consider the curve 3. So as in this case, our target strength is somewhere around 48 megapascal. So we need to consider it lies between 43 and 53. So we have to consider curve 2. So that means you somewhere 48 will be here. So approximate I need to go here. So 48 is somewhere here. I need to go here. So somewhere it touch here. Then the corresponding x-axis value will be my water to cement ratio. So in that case, I am getting my water to cement ratio value will be somewhere 0.36. I think you got this, how I have calculated my water to cement ratio value. Now you have finalized the water to cement ratio. Then the next step is I need to check whether it is meeting my criteria or not. So for that reason, I need to refer one more code, that is IS 456-2000 table number 5. because that will enable me to check with the environmental condition or the exposure condition. So in this case, in our question it is given the exposure condition is severe RCC. You can see here there are different exposure conditions are there, mild condition, moderate condition, severe, very severe and extreme conditions are there. And that is also applicable whether you are designing for plain concrete or you are designing for reinforced concrete. So in this case, our question it is given severe RCC. That means we need to consider the severe RCC part. And severe means the exposure is severe and we need to take the RCC. That means we need to take these three values. That means your cement content, minimum cement content is 320 kg per meter cube. Then your maximum free water to cement ratio is 0.45. Minimum grade is M30 grade. Let's see. So all these things are written in the red one. Whatever you got it from your table number 5 of your IS 456-2000. So that I have read in the red color ink. So maximum water to cement ratio is 0.45. Minimum cement is 320 kg per meter cube. Minimum grade is M30. So that I got it from here. Severe and it is given RCC. So the corresponding value only I have written here. Now I need to check whether it is meeting my criteria or not. So in that case I need to check maximum water to cement ratio. It should be, I should take 0.45. Then how much I got from my figure? I am getting 0.36. That means it is within the range. Second thing is minimum grade of concrete. So here in this case, minimum grade should be M30 grade of concrete as per this exposure condition. But I am designing for M40 grade of concrete. That means both maximum water to cement ratio as well as minimum grade of concrete, it is satisfying my, whatever the value I got, it is satisfying within that limit. So that's why water cement ratio, whatever I am getting, it is 0.36 is less than 0.45, hence it is safe. That means whatever you have identified till step 3 is correct. It is not 0.29, it is 0.36. It's just a typographical error. Next is, once you find out this water to cement ratio, we need to calculate how much selection of water content, how much water I need to use it. So for that reason, I need to refer table number 4 of IS 10262. So table number 4 says how much is your maximum size of aggregate. So in this case, question it is given maximum size I have taken 20 mm. So corresponding water content will be 186 kg. So you can see, so my nominal maximum size of aggregate is 20 mm and water content, the corresponding value I have taken 186 kg. But whatever value you got it, say for example in your question it is given, say your nominal maximum size of aggregate is 40 mm and you are getting a water content of 165 kg. That value, whatever the value, corresponding value you got, that is applicable for a slump value of 50 mm. And in the codal provision, it is saying for every change or every 25 mm extra slump, you need to add a water content of 3%. That is from the codal provision. So these things you need to remember so that you can do a error-free mixed design. As our slump value is given 75 mm, but this 20 mm size of aggregate, so whatever the water content 186, it is applicable for 50 mm size of aggregate or 50 mm slump value. So how much extra slump is required? You have in the question it is given 75 mm and whatever 186 kg water content you got, that is applicable for 50 mm. That means 75 minus 50, that means 25 mm extra slump is required. And as I said, for every extra 25 mm slump, you have to add the water content of 3%. That means 3% extra water I need to add in my mixed design whenever I am going to calculate my water content. So 186 because you got 20 mm maximum size of aggregate and water content in 186, that's why 186 plus how much extra water is required, 3% of 186. So I am getting water content of 191.58 kg. This much water is required. But here there is a change is there, because again in the question it is given superplasticizer also you are adding in the mixed design. So because superplasticizer also contains water, so that's why you have to reduce the water content, because as I said superplasticizer also used for the water reduction. So in that case question it is giving superplasticizer and as you are using normal, that's why it has a reduction of 23%. And whenever you are going to calculate the superplasticizer dosage, basically we need to consider 1% by weight of cement. So in that case you already estimated the water content, that is 75 mm slump, okay, and you are getting water content of 191.58 kg, and as 23% water reduction is there, so how much reduction, how much left out water will be 0.77. From 100 you can reduce to 23, so you are getting 0.77. So the final water content I am getting 148 kg. So that is how you can find out the water content. That means superplasticizer also you have taken into action. So that's why from the water content you have deducted the superplasticizer content. So that is that how much water I am going to add it. So all this individual I am going to consider one by one. The next step is I am going to calculate my cement content. Now my water is already been finalized. How much water I am going to use it. Now the next one is I am going to calculate how much cement I am going to use it. So cement, for that I have already calculated my water to cement ratio in the step 3. So I have already got 0.36. Now how I am going to calculate the cement content? Water to cement ratio I have taken 0.36. So water will be, if you just have a cross multiplication, 0.36 into C. So that means, because already you have identified the water in the previous cases. So what you will do? So water means you have already calculated water is 148 kg. So 148, this 0.36 if you divide there, so you will get a cement content. So 148 divided by 0.36, you will get a cement content. So same thing, I am getting my cement content is 412 kg per meter. So my cement content is also, I got it. Now the next thing is similar to that of your exposure condition. I also need to check whether my cement whatever I have taken, whether it is meeting my criteria or not. So that's why from the table 5, as you can see in the earlier slides I have shown you, my cement was missing from that. So cement, minimum cement you have to use it 320 kg per meter cube. So in that case, what I am getting my cement content is 412 kg per meter cube. That means whatever the cement I have taken, it is also meeting my exposure condition, because minimum you have to take 320 kg per meter cube, and I have taken cement content of 412 kg per meter cube. That means it is also satisfying my exposure condition. Hence it is okay. So the next step is step 6. Because as of now I have calculated my cement content, I have calculated my water content, and the next is I need to calculate my volume of coarse aggregate and fine aggregate content. That is most important. So in that case, I need to refer table number 5 of IS 10262/2019. So what I am going to check? I need to check the corresponding, because I have a maximum size of aggregate is 20 mm and it is applicable for zone 2 it is given. So let's see. So you have maximum size of aggregate 20 mm and it is given in the question, you have to use it. The zone is zone 2. So my coarse aggregate part is 0.62. You should remember that this entire table is applicable for water to cement ratio of 0.50. But what you have taken? You have taken the water cement ratio of 0.36, because that is what you have derived from your graph, right? So water to cement ratio you are getting 0.50, because for this case how much you are getting coarse aggregate volume? Coarse aggregate volume you are getting 0.62. Again I am repeating, because 20 mm maximum size of aggregate, it is giving zone 2. So the corresponding value I am getting coarse aggregate volume will be 0.62. Okay. Now you are getting coarse aggregate volume is 0.62. But this is applicable for water to cement ratio of 0.50, right? And in this case, you are taking an actual water to cement ratio, what you derived from your graph, step number 3. You are getting actual water to cement ratio is 0.36, right? If you are getting water to cement ratio 0.36, that means there is some kind of deficient amount of coarse aggregate is required. So that means 0.50 minus how much is the actual water to cement ratio? That means 0.14. So here also, like your water to cement ratio, you have a guideline, like for every 25 mm slump, extra slump, you have to add 3% of water. Similarly, here also aggregate you have a codal provision. That means for every plus or minus 0.05 change in water to cement ratio, either you have to increase or decrease the aggregate content by 0.01. So keeping that thing in view, how much extra aggregate is required, you need to calculate. So first one is deficit amount. So 0.14 divided by, for every change of water cement ratio 0.05. So divided by 0.05. How much you are going to add or decrease? 0.01 into 0.01. So you are getting, so how much excess amount of aggregate you are going to add. Okay. So if you do the total volume of coarse aggregate requirement, because this thing you have derived from the table 5, 0.62 volume plus extra coarse aggregate is required is 0.028. So you sum all these things, you are getting 0.648. So you are getting your volume of coarse aggregate by volume, you are getting 0.648. If I am subtracting, I am considering entire aggregate as a 1, and in that I am separating this 0.648. So I will get my fine aggregate content. So from 1, if I am subtracting my 0.648, I am getting my fine aggregate is 0.352. So all this volume of fine aggregate and coarse aggregate, I got it from the step number 6. Okay. So what we understood from this, so we have designed target strength from the step 1, then we have designed air content from the step 2. Third is we have designed a selection of water to cement ratio, that is most important, because from this water to cement ratio, how much quantity of water you are going to use it, and selection of water content, how much you are going to add the water content. In that case, you have to check how much from the codal provision, what is the slump value is there, how much excess slump is required. Say every 25 mm slump I need to use 3% extra water content. And again, don't forget, here you need to use or you need to subtract the superplasticizer content, because superplasticizer also contains some kind of water. Okay, and solid contents are also there in superplasticizer. The next, we have selected any kind of how much cement is required, and the lastly we have also considered the how much volume of coarse and fine aggregate is required for your particular mix. So this is not completed as of now, because one more thing is there. You have identified all these ingredients. You have from the step 1 you have identified how much target strength I need to do. In the second step you have calculated how much air content you got it based on the maximum size of aggregate. The third step is you have identified the selection of water to cement ratio based on the curve. If it is, say for example, curve 1 you have to take, it should be 33 to 43 megapascal. If you are taking curve 2, it should be 43 to 53. And curve 3, if it is, your target strength value will be, say for example, more than 53 megapascal. So in that case, you have to take the curve 3 value. After identifying the water to cement ratio, you need to check whether the water to cement ratio and whatever the design you are doing, whether it is meeting as per your exposure condition or not. So if it is not satisfying, that means you have encountered some kind of mistake or you have done some kind of mistake in your mix design. Then after find out this water to cement ratio, you need to check the selection of water content. How much water I am going to add. Okay. So for that reason, as I said, you need to calculate your what is the workability value is there, and based on that workability, whether you need to add excess water, you are going to add it. For that you can use a codal provision that for every 25 mm extra slump, you have to add 3% of water. And again, you have to subtract the superplasticizer. If it is case, say for example, your normal superplasticizer is there, so it has a water retention of 23%. Say for example, you are designing for a high strength concrete, so in that case water retention will be 30%. So accordingly you have to use, because when you are designing for M80 or M100 grade, like a high strength concrete you are designing, it has a more water retention you have to use. So in that case PC normal may not be applicable in that case. So you can go with PCE advanced version, like superplasticizer advanced version is there, polycarboxylic ether base you have to take it. Then next, after selection of water content, we have identified the cement content from this. So like cement content, you need to calculate, like water to cement ratio already you identified from a previous. So water is already known to you, and your cement value you need to calculate. So water to cement value is already there, ratio is there. So if you need to have a cross multiplication, you can identify the cement content. Once you identify the cement content, the next step is you need to check with the exposure condition, whether the exposure conditions are meeting with your criteria or not. If say for example it is not meeting with the criteria, then again you need to go back, check, and where you made some kind of mistakes. Then the last stage is we have identified the water, we have identified the cement content. The next is the coarse aggregate and fine aggregate volume. So in that case you have to take the table number 5 you have to consider. Maximum size of aggregate is given and C1 analysis zone 2 is given. So accordingly you can calculate the what is the volume of coarse aggregate. Directly you are getting. But this value is only applicable to your water to cement ratio of 0.50. So, but whatever you got the water to cement ratio, you are getting lesser than that. You are getting 0.36. That means how much deficient amount is there? So, 0.50 minus 0.36. That means you are getting 0.14 is the deficient amount. Again, here like your water content, you are going to have a codal provision. Similarly, here also aggregate you will have a codal provision. Every change of water to cement ratio 0.05, you have to add or decrease the coarse aggregate by 0.01. So in that case, you have to do the deficient amount divided by 0.05, because that is the change in water to cement ratio. Then you have to multiply how much excess aggregate you are going to add it, 0.01. So this means you are getting a how much extra excess aggregate I am going to use it. Once you got the excess aggregate, how much you are going to use it, then you have to add with the, you have earlier, I have already find out the, based on the 0.50, what is the volume of coarse aggregate, then you are going to check with the final value. So you are getting the volume of coarse aggregate you are getting. If entire, if I am taking, consider as a 1, like aggregate as a 1. So if I subtract from the 1 coarse aggregate, you are already getting, so minus 1 minus coarse aggregate, you are getting the fine aggregate content. So that as of now we have done in this particular video. So next part of the video, you will calculate how much all the ingredients are required. But for meter cube, whenever we do go for the practical application, we never say this much kg you required, or this much fine aggregate is required, or this much coarse aggregate is required. We need to calculate per meter cube how much ingredients are required. And again we will also discuss about what is the field corrections, because field correction is very much essential. So field correction, why is it essential? It is because like field corrections only, it will identify whether it is a dry condition or a wet conditions. Because if there is a dry conditions, because what happened basically, you see in the picture, the aggregate from the surface you can see, or from the outside covering you see there is no moisture, but inside you see there is a moisture available. So that means it has some kind of, because atmosphere has some kind of moisture, it will ingress, basically it will ingress in the sand, okay, but some kind of moisture also ingress in the aggregate also if it kept outside. So that is why we required a field correction, because whatever you identified the mixed design, how much meter cube you are identified, again there will be a requirement in the field whether you need to do dry conditions or wet conditions, okay. So that thing also very much essential. Now I'll tell you how you are going to check whether this is a dry condition or a wet condition. You need to go back to your question. So say for example in this question, you see here moisture content of aggregate is nil for both the coarse aggregate and fine aggregate. If your moisture content of the aggregate is nil, so that means it is a clear indication of it is a dry condition. Let's say example, if your moisture content of aggregate is given in the question, then that means moisture has already ingressed to your coarse aggregate and fine aggregate. So in that case, it is a clear indication of a wet correction you need to do. So there is two different methods are there. You have a dry corrections method and wet corrections. So all these things you need to identify from this moisture content data. If moisture content data, both coarse aggregate, fine aggregate is nil, then it is a clear indication, that means it is a dry state. So dry state, there is a different formulas are there. For a wet condition, there is a different formulas are there. So all these things we will discuss in the coming slides. Okay. So all the best. If you have any doubt, you can also reach out to me. You can also ping me in this. You can also comment here. Okay. Thank you so much.